Where does coherent light, the light from lasers, fit into your calculations?
The laser has to do with the fact that watch. We spoke about this situation and this situation, only this time I'm going to call it photons. Suppose that you have two sources, or two atoms, 1 and 2, which can emit a pair of photons, and you want to know, do you get a photon in two different counters, 3 and 4? There's two ways that can happen. But this time, because it's photons, we're supposed to add these two. Now, if these atoms are in the same condition, or very close, then the amplitudes that we're adding are virtually equal. So the amplitude for the event that the two atoms which are ready to emit produce two photons is twice as big as you would have guessed. If the two photons were different, you would just get this one term because you could distinguish this case from this one. But the two photons are very much the same. You have to add this other amplitude, which is the same thing except that instead of E's, they're P's. And if 0.1 and 0.2 are close together, or in the same condition, you have to add two numbers which are the same, and therefore double the amplitude and multiply the rate by 4. So therefore, the rate at which two atoms will emit light, if they emit the same light, is higher than if they emit different and independently. So when there's a large number of atoms, the same thing happens. You have to add all the combinations. And when you have a whole lot of atoms which are all set to emit, that can possibly emit the same, exactly the same kind of photon, they emit much more with a greater enhancement. They all cooperate to emit. They emit with a much higher probability than you would otherwise expect. A laser is a device for producing a large number of atoms in a corresponding physical state which are all capable of emitting a photon in a particular direction, one kind of photon. It corresponds to all the 3s and 4s being on top of each other. And it has, therefore, when they're all in the right condition to emit, a whole bunch of them discharge their energy into the same photon, and that's what you call the coherent light of a laser. It's a very intense light of a single frequency in a single direction. The reason it works has to do with this interference. It's not a very good answer, but it might give you a clue.
Does the amplitude of a photon coming out have any effect on the one going in?
Yes. What we have to do is we have to work out. You remember when I cheated in the beginning, when I was doing this easy, I said all you do is you take the time it took the light to get from here to here. But you see, that really is the sum of two times. I could analyze it in two steps. I could say there's a certain amount of, there's an amplitude that you come out, amplitude that you reach here, amplitude that you reflected times amplitude that you get here. Now, in multiplying the amplitude to go from here to here by the amplitude to go from there to there, I add those two angles. So I add the angle for this time to the angle for that time. It's just the angle for the total time. So that I can analyze this either way. I can either think of it as one photon doing that and consider the total time it went, or I get the same answer if I think of a photon went from here to here, a certain change in amplitude, angle. Then a photon, new one, goes from here to here. That would contribute an angle too. But I say to multiply them in succession. And when you multiply, you add the angles, and that's equivalent to the total time. So it comes to the same answer.
Does the existence of a positron involve some sort of violation of causality?
No. The question was that my description of the positron here involved apparently some sort of interaction, and yet an electron can be all by itself. That was a completely unnecessary difference. There's not an essential difference. I explained the need for the positron by a kind of continuity from this diagram here to this case here, in which the timing is changed, and told you that this function, mathematical function, had to be, this E function, has to be of a certain form where it's completely smooth between here and here. In fact, the mathematical properties are that the behavior when 6 is later than 5 and 6 before 5 are very closely interconnected. One can deduce one from the other. That's all I wanted to say about that. There's no reason why this backwards moving section cannot be a long section, either interacting with photons or not. I gave you an illustration of one where it was a long time going interacting. But it could be that this positron was made on some star 10 light years away, and it's been going this way in empty space, unperturbed by any photons in the neighborhood, disturbing it or be picking them up or not, like it was an electron alone in space for 10 years. Okay? So there's no reason why positrons, in fact they do, they last, they behave exactly the same as electrons. But for the accident of the fact that the world has so many electrons, the matter in the world has so many electrons in it, so our laboratory walls are full of electrons, and we can't make the positron not hit a wall. If it's left alone, it coasts into the wall. And when it coasts into the wall, it annihilates. So in practice, the positrons don't last very long. But if you get them in a circumstance where there's no matter, we have done so. It's not left alone because of the wall. But you can make them go in a circle by using a magnetic field. And then you can keep them going for days, going around in a circle, untouched by human hands, not touching any electrons, and they stay, and they stay, and they stay. In fact, we do experiments by making speeding up positrons going around in a circle to a very high energy, and making electrons go in the circle in the opposite direction, and looking at what happens when the electron and the positrons collide with each other. Then we have a diagram that starts out like this. Electron coming in, positron coming in. Time is this way. And then things happen. Photon comes, and then one thing might happen is a pair of new particles might come out. If you want to know what kinds of new, could be an electron and positron, it's uninteresting in coming out in a new direction. You would think that just means a collision. But really what it was an annihilation followed by a recreation. But even more interesting, and I will advertise the next lecture, there are other particles in the world, and this is one way to make them. We can make particles called muons by hitting electrons and positrons together and producing a pair of something else. Mu plus and mu minus. So there's nothing different about a positron and an electron. They're all very symmetrical, except history, except the characteristic of our laboratory, that we have a superfluity of electrons. We have an excess of electrons.
Is the direction of time in your laboratory reversible then?
It's a very interesting subject and requires a lot of more serious discussion. His question was, what about the time in your laboratory? Is it reversed? The order of time, that is to say, the order of events like this, if you put hot and cold things together, then it gets lukewarm. But if you take two lukewarm things and put them together, one doesn't get hot and the other just gets cold all by itself. The explanation of that direction of time, has to do with the confusion of things. If you would take a lot of black things and white and black objects and then just jiggle them, they get mixed up into gray. If you start with gray and just jiggle them, they never get black and white. But each jiggle could be perfectly reversible. For instance, your rule could be just take a pair and flip them over. Take a pair and flip them over. You can't tell whether I'm going forwards or backwards in time. If I take a pair and flip them, that is, reverse them, it looks exactly the same. If I ran the movie picture backwards, I took a pair and reversed them. So therefore, what is interesting is, it turns out that on the microscopic scale, all the laws of physics are exactly reversible. Forwards in time, backwards in time look the same. But all those phenomena, and there are many, of course, life and frying eggs are two examples, which go in one direction only in time, have to be interpreted by the complexity of the circumstances, that there are so many particles getting mixed up, plus some assumptions or understanding about the fact that in the past, the matter in the universe was at a higher density than in the future. This is a property of the universe at large and is not reflected in the microscopic laws. So it does not, it turns out, in spite of the fact that I draw my arrows upside down, end up violating any causal principle. Strangely, it is very interesting.
Whenever you have shown an electron changing direction in your space-time diagram, it has coincided with a junction. Why?
I did that because what I really know, and only thing I do know, is that there's an amplitude to go from 0.5 to 0.6 as a free particle without disturbance. And then there's junctions, and then it goes to another point as a free particle without disturbance. And so I just wanted to represent the functions which I've erased here. By this line, I mean that in the final expression you will find a factor E56. The line is only meant to indicate that fact, the fact that it's straight is a convention. All right? It doesn't mean that the electron has to go exactly along here or anything like that. All I know is it's generated as 5 and disappears at 6. And it has amplitude E56. Okay? I don't worry about where it actually went.
A disturbance has to travel from 5 to 6 then.
Well, 5 and 6 are the places in which the photon, in this particular case, is coupled. I have only 3 things. It goes from one point to another in a leap, a pure leap without disturbance. The amplitude to do that is that E. Photon goes from one place to another without disturbance. The amplitude to do that is the D. Then there's an amplitude that an electron and a photon and another electron come together at a point. That's C. The 3 rules of nature, or quantum electrodynamics. If all of nature isn't that would be all there was to it, but that's all there is to the part that we need to do quantum electrodynamics.